I want to be able to pick any number in here and figure out what the likelihood of that number is. Now, by empirical rule, I could easily take and say if we have a value of something like 0.6, given that this is 1/2, we could come up with a value for how likely it would be to see 0.6 or less, or something more than 0.6, and that would be areas based on empirical rule, or it would be areas based on a normal distribution. So when we do that, calculate this out. So this is 1/4, right? Or 0.25 divided by 25 and the square root, and that is equal to
0.5. 0.5 over 5.
Yeah, 0.5 over 5, 0.5 over 5, but that's going to be 0.1, square root of 0.1. Is my math working out right? Oh, I already took the square root of it, didn't I? So this works out to 0.1. Okay? We do have to do some math once in a while, right? And you can see how good I'm at it. I'm very bad at doing math in my head. That's why I use computers for it. So this is going to be 0.5. Approximately, we would have values here. So this is going to be 0.6, 0.7, 0.8, something like that. Okay? If I then take and consider a particular sample that's coming from the population that has a P of 0.5, and I want to find out how likely it is that I would see that or something less or greater than, depending on how we want to look at it. So let's take some specifics. What if we said that we come up with a value of 0.4. 0.4 is about the proportion of males at Grand Valley. So if we come up with an observation of 0.4 from a sample. So my observation then is at this point right here. Interesting questions about that observation might be, how likely would it be to see something that is that or farther away from 0.5? Why would I do something like that? If I say that the true population is 0.5, I say that this sample that I've taken has a proportion of 0.4. It's a sample from the underlying population. I'm going to want to make inferences about this, aren't I? Those inferences can be confidence intervals or hypothesis tests. And one thing that you might want to do is determine if the observation that you've taken is sufficiently unlikely that you would say that it contradicts your original assumption. Your original assumption is that the population has a proportion of 0.5. So an observation of 0.4, if you want to find out how likely that would be to be that far or farther away, well, let's just take it as that small or smaller. So if we look at what is the likelihood of seeing 0.4 or less, if in fact the population is centered at 0.5. So how would we do that? By empirical rule, can we do that? What would that be by the empirical rule?
1 minus 0.68.
We know that this is 0.68 here.
So then divide that by 2.
Yeah. 1 minus 0.68 would be 0.32, right? Half of that's here, half of it's over here. So this must be 0.16, and this is 0.16 over here. Okay? That's just by empirical rule. What that says is that by the empirical rule, we ought to expect about a 16% chance of seeing a 0.4 or less from this population. Okay? That seem quite likely? Does 16% seem likely that you'd see 0.4 or less? It's going to depend on something though, isn't it? It's going to depend on the size of the sample. So let's get a little bit more accurate here. How do I get this to where I can look something up in the textbook? How I can look up an actual probability? Now, sometimes I worry about showing you guys this because it's a little archaic, but it does help to illustrate a little bit of what actually goes on in calculating these probabilities. Nowadays, if you had a calculator, I could plug 0.5 into the calculator, 0.1 is the standard deviation of the calculator, and ask it for the probability of 0.4 or less, and it would just give me the value. I wouldn't have to go through all of this. But this will help to see a little bit of what's going on. In the back of your text, Table 8.1. This is the table in the back of your text. It's actually inside the back cover. So it's Appendix 8.1, but it's also the back cover of your text. It's 2 pages. Table 8.1 is for Z distributions. This thing over here is a normal 0.5, 0.1. This thing is a 0, one distribution. This is what's called a standard normal. Okay. These values are 0, 1, 2, 3, minus 1, minus 2, and minus 3. Okay. If you look back in your text in chapter 8, it talks about a Z transformation. It talks about a Z transformation in this form. An observation minus the mean divided by the standard deviation. In this particular context, that is our observation p hat minus p divided by the standard deviation. What that is it transforms values from this distribution into this one. So this numerator shifts this 0.5 over to 0. The denominator of this thing takes the width of this and transforms it into exactly deviations of 1. This is actually measured in standard deviations. Okay? And this is Table 8.1. Table 8.1 gives us areas to the left of values in this distribution. If we look at this 0.4, go through the Z transformation, Z is equal to 0.4 minus 0.5 divided by 0.1. So that is equal to minus 0.1 over 0.1 or minus 1. Okay? So here it was minus 0.4, or actually it was the value of 0.4. Here it's going to be minus 1. So right here is the value we're looking at. And what we want is that area right there.